Modern warfare is no longer defined by raw firepower alone, but by the interaction between sensors, networks, decision-making speed, and system resilience under pressure. At the global strategic level, every regional confrontation feeds into a wider system of deterrence, signaling, and power balance. The Middle East represents one of the most complex and densely monitored military environments on the planet. Geography here compresses reaction time, leaving minimal margin for error in both offense and defense. Iran's military doctrine does not attempt to mirror U.S. capabilities symmetrically. Instead, it deliberately exploits asymmetry through cost efficiency, terrain familiarity, and operational ambiguity. In this model, a single missile is not designed to win a war outright. Its true function is to stress, probe, and degrade an opponent's defensive system. Iran prioritizes survivable and mobile launch platforms over fixed installations. Mobility statistically reduces detection probability and increases launch survivability. The Khalij-e Fars missile is a clear embodiment of this operational philosophy. Its design emphasizes reliability and rapid deployment rather than technological excess. Solid fuel propulsion allows the missile to launch with minimal preparation time. This dramatically reduces vulnerability during the pre-launch phase. Once airborne, the missile follows a quasi-ballistic flight profile. Ballistic trajectories trade maneuverability for speed and kinetic efficiency. At these velocities, kinetic energy becomes a primary destructive mechanism. Mid-course guidance relies on inertial navigation systems, governed by continuous error correction. Small deviations accumulate mathematically and must be corrected in real time. Accuracy, therefore, is achieved statistically rather than absolutely. The Persian Gulf is a geographically confined battle space with limited maneuver room. Short engagement distances significantly reduce detection to intercept timelines. Naval targets operating here often follow constrained maritime corridors. Khalij-e Fars is optimized to exploit this predictability. Its electro-optical and infrared seeker activates in the terminal phase. Infrared contrast over open water simplifies target discrimination. Thermal signatures are governed by physics and cannot be masked easily. The missile's warhead prioritizes penetration rather than blast radius. At hypersonic adjacent velocities, impact force scales exponentially with speed. Mass multiplied by velocity becomes destructive energy. During re-entry, the missile experiences extreme aerodynamic heating. Plasma formation around the body complicates external radar tracking. Internal thermal shielding ensures seeker and guidance survivability. In the terminal phase, the missile deliberately limits excessive maneuvering to preserve structural integrity, ensuring stability rather than acrobatic precision. Fewer moving control surfaces mean fewer mechanical failure points under extreme thermal and aerodynamic stress. Iranian missile doctrine does not seek perfect accuracy in the Western sense of surgical strikes. Instead, it focuses on achieving a statistically sufficient probability of hit within a constrained battle space. In this framework, precision is replaced by reliability and repeatability. One missile represents a tactical threat, but multiple missiles redefine the engagement entirely. When launched in volume, even modestly accurate weapons impose disproportionate pressure on defensive systems. This is the core principle of saturation warfare. Defensive systems must succeed every time, while attackers need only one success. That asymmetry fundamentally alters cost and risk calculations. Mobile launch platforms further complicate preemptive countermeasures. Once a missile is fired, the launcher rapidly relocates to avoid detection and retaliation. This creates a time lag between launch detection and counterstrike feasibility. In most scenarios, the engagement begins after the attacker has already withdrawn. Decision-making windows compress to seconds rather than minutes. Under such constraints, human and system latency become decisive factors. The Persian Gulf offers almost no spatial buffer for error correction. Every kilometer reduces interception probability. Every second increases uncertainty. Physics enforces these limits regardless of technology. Speed, distance, and geometry dictate outcomes. Khalij-e Fars is designed specifically to exploit this unforgiving environment. Its simplicity is intentional, not accidental. Fewer subsystems mean higher operational confidence. Lower production cost enables sustained deployment. Sustained deployment creates persistent pressure, and persistent pressure erodes even advanced defenses over time. To counter such threats, the United States relies on a layered, network-centric defense architecture. At the heart of this architecture lies the Aegis combat system. Aegis functions not as a single weapon, but as an integrated decision-making ecosystem. The SPY radar continuously scans, tracks, and prioritizes hundreds of targets simultaneously. Raw radar returns are filtered through predictive algorithms to reduce noise and false positives. Each tracked object consumes processing bandwidth and attention. Under saturation, resource allocation becomes critical. The SM-6 interceptor serves as the kinetic extension of this network. Unlike purely ballistic interceptors, SM-6 retains high maneuverability throughout flight. Its solid fuel motor provides sustained thrust rather than a single boost phase. Thrust vector control allows rapid directional correction at extreme G-forces. Intercept solutions are recalculated continuously in real time. The missile does not chase the target. It predicts where the target will be. This prediction is governed by probabilistic mathematics, not certainty. Every intercept attempt carries a calculated probability of kill. That probability is never absolute. Each SM-6 launch consumes a high-value asset. Missile inventories aboard ships are finite and irreplaceable during combat. At sea, reloading vertical launch systems is effectively impossible. Thus, every defensive success also reduces future defensive capacity. This creates a strategic trade-off between immediate survival and long-term endurance. Saturation attacks exploit this imbalance deliberately. Even advanced radars have tracking limits. Command teams must prioritize which threats to engage and which to accept. These decisions occur under extreme time pressure. Cognitive load increases exponentially during high-density engagements. Stress amplifies the likelihood of error. Final intercept windows may last only seconds. Fragmentation warheads compensate for small guidance inaccuracies. Proximity detonation increases the lethal envelope. Yet interception remains a statistical outcome, not a guarantee. A single failure can alter the entire tactical picture. Defense systems aim for resilience, not perfection. Resilience depends on redundancy and discipline. Discipline depends on training and doctrine. Doctrine depends on strategic assumptions. Those assumptions are constantly tested in real-world operations. Missile defense success is measured cumulatively, not individually. Attrition slowly reshapes the balance of power. Time favors the side that manages resources more efficiently. Efficiency becomes a strategic weapon. Systems fatigue even without catastrophic failure. Maintenance cycles grow shorter under sustained alert. Crew endurance becomes as important as hardware performance. Human factors increasingly dominate outcomes. Advanced technology cannot remove them, only mitigate them. Defense becomes a long-duration contest, not a single decisive moment, but a continuous test of endurance. At this stage, the confrontation clearly transcends individual missiles and isolated engagements, evolving into a full-scale interaction between opposing military systems. What unfolds is no longer a duel of weapons, but a contest between doctrines, architectures, and operational philosophies. Iran's approach emphasizes dispersion, mobility, and the ability to strike repeatedly under constrained conditions. The United States, by contrast, relies on integration, precision, and real-time coordination across multiple domains. One strategy leverages volume and persistence to overwhelm defenses. The other leverages computation, sensor fusion, and predictive engagement. Despite these differences, both sides remain bound by the same immutable physical laws. Distance, velocity, and time govern every engagement geometry without exception. As missile speed increases, reaction windows compress accordingly. Simultaneously, even minor tracking or prediction errors expand non-linearly. Saturation tactics are designed specifically to exploit these expanding margins of uncertainty. Under sustained load, defensive performance curves inevitably flatten. Each successful interception consumes finite resources and reduces future flexibility. Over time, attrition favors strategies that achieve effects at lower cost. Cost per effect thus becomes a decisive strategic metric rather than a logistical detail. Networked sensors and data fusion reduce uncertainty, but they can never eliminate it entirely. Information dominance delays failure rather than preventing it. Eventually, even the most advanced systems approach exhaustion. Iranian doctrine explicitly targets this long-term degradation process. The objective is not immediate destruction of high-value assets. Instead, it is the gradual erosion of defensive endurance and confidence. Every alert cycle consumes crew attention and readiness. Every intercept drains missile inventories and processing capacity. Even flawless defense carries an inherent strategic cost. In modern conflict, victory rarely arrives in a single decisive moment. It accumulates incrementally through sustained pressure and adaptation. This dynamic defines what is known as system-level warfare. Individual missiles function merely as variables within a much larger equation. Doctrine determines how those variables interact over time. Geography imposes constraints that no technology can fully overcome. Narrow maritime spaces eliminate depth and buffer zones. Sensor networks saturate faster in confined environments. Decision timelines compress to their practical limits. Errors propagate rapidly across interconnected systems. Iran designs its forces to survive and operate within these constraints. The United States designs its forces to dominate through integration and coordination. Both approaches encounter diminishing returns as engagements persist. The balance of advantage shifts dynamically rather than decisively. Escalation resets key variables without resolving the underlying equation. Each new weapon system alters engagement geometry only temporarily. Continuous adaptation becomes a necessity rather than a choice. Every system deployed invites the development of a counter-system. Every defensive improvement invites a corresponding workaround. This reciprocal cycle defines contemporary military competition. Technology accelerates the pace of this cycle. Strategy frames its application. Mathematics governs its outcomes. Reality enforces its limits. No participant escapes the laws of physics, and no complex system escapes entropy. At its core, the central question is not who prevails in a single engagement or isolated confrontation. The more consequential question is who adapts faster across repeated cycles of action and response. Iran seeks advantage by exploiting environmental, economic, and operational constraints. The United States seeks advantage through scale, redundancy, and integrated command structures. This confrontation operates at the strategic system level rather than the tactical level. Individual battles reveal only fragments of the broader dynamic. Missiles function as strategic signals as much as physical weapons. Intercepts function as calculated responses within an ongoing exchange. Every launch and interception generates valuable operational data. Each dataset feeds directly back into doctrine, design, and training. As a result, future engagements will rarely resemble past ones. New variables will continually reshape the battle space. Hypersonic systems further compress already narrow reaction timelines. Directed energy weapons may eventually alter cost exchange equations. Artificial intelligence increasingly shortens decision loops. Meanwhile, battlefields evolve faster than political or legal frameworks. Capabilities that succeed today may become obsolete tomorrow. Defense is therefore never final or absolute. Deterrence remains dynamic rather than static. At this very moment, mobile launch platforms may already be dispersing. Interceptor missiles may already be loaded into launch cells. Engineers may already be refining engagement models and algorithms. Commanders may already be simulating future scenarios. This is not a single conflict with a clear endpoint. It is an ongoing process of competition and adaptation. Each episode reveals another layer of the system. Each layer exposes new vulnerabilities and opportunities. The question now becomes which weapon will define the next phase, and which defensive system will emerge to counter it. Many of those answers remain classified. Their strategic implications, however, are already visible. Modern warfare is fundamentally a race of learning and adaptation. That race does not pause or conclude. The strategic equation continues to evolve. Variables shift continuously under pressure. Systems remain in constant motion. The balance of power remains unresolved. The confrontation itself remains unfinished. The next chapter is already taking shape, and its outcome will be determined by who understands the system first